Now let us discuss a concept called LC oscillations. If you consider a series resonance circuit, then you see this was a kind of circuit which was used to accept a particular frequency. Let's suppose a signal is coming out from some source of a particular frequency, then RLC circuit or series resonance circuit was accepting that particular frequency. Now try to think of that source, that how is it creating an electromagnetic wave of some desired frequency. So this is the answer. LC oscillation is, you can say, a kind of arrangement which is used to generate an electromagnetic wave of some desired frequency. This setup is used to generate a signal of some desired frequency. You understand? This is the function of an LC oscillation. In this kind of LC oscillation, essentially you have an inductor coil and connected to capacitor. Understand? You have a capacitor and you have an inductor connected to it. The circuit is very much ideal. To understand that the resistance of the circuit, entire circuit, is 0, and the beginning of the circuit happens to be that you put some charge on this capacitor. You can say some energy will be stored on this capacitor. That energy goes into inductor. From the inductor it again comes back to the capacitor, again goes back to inductor, and you can say oscillation of energy takes place. Because of that oscillation of energy, you can also say that oscillation of charge is taking place, and you will be getting to know that whenever a charge is oscillating, it is generating an EM wave. So this energy oscillation comes out in the form of, you can say, an alternating signal of desired frequency. If you want to keep the frequency fixed, then how will you be doing it? Then for that you understand that at any moment the charge which is there on the capacitor is a small q. Maybe in the beginning you have given a larger charge, say capital Q, but at any instant you try to understand that the charge which is there on this capacitor is a small q, and the current which is flowing into the circuit is I. Now if you try to invoke this Kirchhoff's voltage law, then this Kirchhoff's voltage law will say that once you are jumping across this capacitor, there is a potential drop equal to minus Q by C, and the potential drop across inductor that will be taking place, that will be minus L di by dt, and that will make it equal to 0. Now since the current is in itself equal to dq by dt, so you can say that the entire expression which you have here, that can be written as L d2q by dt2 plus q by c equals to 0. Understand? So this is the, you can say, differential equation of oscillation, LC oscillation, which is taking place. I am getting this inspiration of calling it oscillation because if you consider the differential equation of simple harmonic motion, which you call mechanical oscillation, then you can write that m into d2x by dt2 plus kx equals to 0. So you see, this is a differential equation of mechanical oscillation, you can say. And analogous to this mechanical oscillation equation, you have here this equation as electrical oscillation. You understand? So whatever kind of analysis you have made for mechanical oscillation, same kind of analysis will be available for electrical oscillation as well. In the sense that whatever kind of equation, say x is equal to a sin omega t you got here, here also you can have the same kind of expression, charge involving as sine function or cos function. Some of the analogies you can see here, that whatever role mass has to play in mechanical oscillation, same role the inductor has to play. If mass is like inertia, then L is like electrical inertia. जो भी रोल मास का मैकेनिकल ऑसिलेशन में है या मैकेनिक्स में है, वही रोल इंडक्टर का इलेक्ट्रिकल ऑसिलेशन के लिए है. Whatever role this spring constant is playing, same role is being played by capacitance, or inverse of capacitance is working like spring constant, and things like that, say displacement analogous to charge and all that you can think. Now if you further simplify this expression, then remember that you had this omega square as equal to k by m. This was the kind of expression you can say you had for simple harmonic motion. This was called angular frequency. So if you are writing it as k by m, then here you can write it as 1 by c by l, and so you can say that 1 by LC will also be playing the same role, and the angular frequency omega here you will be getting, that will be 1 by under root LC. So for LC oscillation, this is the kind of, you can say, desired angular frequency. Once we said that of some desired frequency, this word you saw, desired frequency, this desired frequency is essentially this. This is having the unit radian per second. In case you want in hertz, then you can say that the frequency can be written as 1 by 2 pi under root LC. And incidentally, this expression is same as that you got for resonance. The resonance frequency also came out to be something like 1 by 2 pi under root LC. So this is the desired frequency you will be obtaining whenever you will be having an LC oscillation. Now if you want to represent the expression of this charge or maybe the current, then now you are free to write down the expression of the current which will be flowing, or the charge which is flowing into the LC oscillation. If let us suppose you want to write down the expression of charge which is present on the circuit, on the capacitor, you can say, for that matter, I can write it as Q naught cos omega t. You may object that why didn't I use the sine function? I could have written as sin omega t as well. This omega is same as what you have obtained here, that is 1 by under root LC. Now see, in the beginning, generally it is the practice that you will be charging the capacitor. That means at t is equal to 0, the total charge should appear on the capacitor. So this is possible only when you have cos function and not the sine function. So once you are putting t is equal to 0, then the maximum charge will be appearing on the capacitor. And for that matter, you can say, if you want to write down the expression of current, then it can be written as I naught sin omega t. This is a kind of variation you will be having so long as this charge or this current is concerned. Now if you talk about the energy, then remember that whenever the total charge is there on the capacitor, then it's only the electrical energy which is there in the circuit, because in the capacitor the energy is stored in the form of electrical energy. But जब भी current inductor में flow करता है, then you have seen that there is a energy involved in the inductor as well, half Li square you have seen, and that energy happens to be in the form of, you can say, magnetic energy in the circuit. So some of the questions may be asked to you that at what time the energy is purely electrical, at what time the energy is purely magnetic. So let us have a discussion over that. Let us suppose we are demanding that at what time energy is purely electrical. Then you see, as we have seen, that energy will be purely electrical whenever the charge is completely stored on the capacitor. Electrical energy is involved with the charge. If you are having, you can say the expression of charge as Q naught cos omega t, and if you are trying to plot this expression of charge as a function of time, then it will be something like a cos curve. You understand? And as you know that as a function of time, you can say this is the complete cycle you have at this moment, and at this juncture the half of the time period has been consumed, and if you again come to this side, then the time can be written as 3t/2. You see that energy in the circuit will be purely electrical whenever the charge will be having the maximum value. And from this diagram you can see the charge is having its maximum value at t is equal to 0, or at t is equal to t/2, or at total time capital T, or 3t/2, and so on. So the answer will be energy will be purely electrical at t equals to 0. That means जब आपने सर्किट को स्विच ऑन किया होगा उस समय भी एनर्जी प्योरली इलेक्ट्रिकल है, बिकॉज इट इज एक्सपेक्टेड दैट यू आर गिविंग द इंटायर एनर्जी ऑन द कैपेसिटर. देन at time t/2, again the energy will be purely electrical. Maybe the energy initially it was here, it has gone to the inductor, and again it has come back to the capacitor after half of the time period. So there again the energy is purely electrical. Then again at time t, then at 3t/2, and so on. This is the way you can say after every half time cycle, starting from beginning, the energy stored in the circuit will be purely electrical. Now on the similar line, if I am asking at what time the energy is purely magnetic, let us suppose, now I demand the second thing from you, what will you say? The next thing we are asking is that at what time energy is purely magnetic in the LC oscillation. Then you see energy will be magnetic whenever the current in the circuit will be maximum. You are writing the current expression as I is equal to I naught sin omega t. मैग्नेटिक एनर्जी दैट इज इन्वॉल्व विद करंट. तो जब भी करंट की वैल्यू मैक्सिमम होगी उस समय में एनर्जी सर्किट में प्योरली मैग्नेटिक होगी. और अगर हम करंट का वेरिएशन देखें, it is essentially a sine function, then it is having a variation like this. You understand? Now you see this was the point 0, but this time will be t/4. Understand? t/4. This is quarter cycle spent when you will find that the value of current has become maximum. Then here you will be having 3t/4. When again you will find that the current has become maximum, then again you happen to see that the current is maximum at time t 5t/4. So these are the times when the energy will be purely magnetic, because the current that time in the circuit that is having maximum value. So answer will be at t is equal to t/4, at t is equal to 3t/4, at time is equal to 5t/4, and so on. These are the times when you will have energy completely magnetic involved in the circuit. You understand? Now connected to this LC oscillation, we may ask some other question like this. For an LC oscillation, like this you have, it is given that voltage rating of the capacitor is V. voltage rating of the capacitor is V, then find the current rating. Find the current rating for the inductor. You understand? This is my question. आपको एक LC ऑसिलेशन के लिए उसके कैपेसिटर की वोल्टेज रेटिंग दी गई है. दैट मीन्स द मैक्सिमम वोल्टेज दिस कैपेसिटर कैन सस्टेन, and then you have to find out the current rating of the inductor. That means what is the maximum current which can flow into the inductor. Then for this kind of situation, remember that the entire concept is involved with the energy stored in the circuit. जितनी एनर्जी आप कैपेसिटर में स्टोर करते हैं वो सारी की सारी एनर्जी, लेट्स सपोज ये कैपेसिटर को आपने वोल्टेज V प्रोवाइड किया, देन सम ऑफ द एनर्जी इज इन्वॉल्व्ड हियर. इस कैपेसिटर में कुछ एनर्जी स्टोर हो गई होगी. हाउ मच ऑफ दैट एनर्जी हैज बीन स्टोर्ड? सो दैट इज इक्वल टू हाफ CV स्क्वायर. दिस इज द टोटल एनर्जी विच हैज बीन स्टोर्ड इन द कैपेसिटर. नाउ दिस कंप्लीट एनर्जी शुड गो इनटू द इंडक्टर. जब आप इंडक्टर का रोल देखेंगे तो इंडक्टर शुड हैव दिस ability to store this entire capacitor energy in itself, and the total energy involved in this inductor can be half Li square. You understand? This is the total energy is stored in the capacitor. This is the total energy involved in the inductor, and that should match. अगर कैपेसिटर की एनर्जी ज्यादा है, इंडक्टर कम एनर्जी होल्ड कर सकता है, then if you try to pump that entire energy of the capacitor into inductor, inductor will burst. Or इट मे बी दी अदर वे राउंड. अगर इंडक्टर में ज्यादा एनर्जी है तो कैपेसिटर कैन बर्स्ट. सो अगर आप यहां से I की वैल्यू निकालेंगे तो यू कैन गेट द वैल्यू I एज V अंडर रूट C बाई L. यू अंडरस्टैंड? द वैल्यू ऑफ करंट, मैक्सिमम करंट विच यू कैन हैव फ्रॉम दिस प्लेस. अगर आपको कैपेसिटर इंडक्टेंस की वैल्यू मालूम है एंड द वोल्टेज रेटिंग ऑफ द कैपेसिटर इज नोन टू यू, देन यू सी that the maximum current which can pass into the inductor that can be calculated from this expression. Another very important aspect to remember about this kind of circuits is that in ideal case the total energy stored in an LC oscillation circuit is constant, and based on which we can ask you some of the questions. Let us see that. Remember that ideally means the resistance is absent. You understand what is the meaning of ideally word here? Ideally का यहां पे मतलब है कि सर्किट में कोई एनर्जी का लॉस नहीं है. Resistance is not available. It's only the capacitor and inductor, they are present in the circuit. Then it says that ideally the total energy stored in the circuit is constant. That also means, let us suppose आपने शुरू में सारी एनर्जी कैपेसिटर को दी थी, तो what was that energy in the capacitor stored? That will be Q0 square by 2C. In case the capacitor had got the initial charge as Q0, then what was the total energy pumped into the circuit in the beginning? That was Q0 square by 2C. Now after some time you have seen that some of the charge has been converted into current and that is passing through inductor, and some of the charge is left over with the capacitor. Then after some time you will find if the energy stored in the capacitor will be written like this, small q square by 2C, then rest of the energy has gone into the inductor, half Li square. And finally you will find that that will be converted into the maximum current which will be flowing through the inductor, and that is half Li max square, or you can say, you had said it to be I naught, then it can be written as I naught square. I max से हमारे यहाँ मतलब maximum amount of current है. So you can say the energy stored in the capacitor goes finally to the inductor, it comes back to the capacitor, energy keeps shuttling and at whatever frequency this energy is shuttling, that decides what can be the frequency of the wave or electromagnetic wave which will be generated from this LC oscillation, and that you have already calculated 1 by 2 pi under root LC. So these are some of the questions which will be asked based on LC oscillations, like at what time the energy is purely electrical or magnetic, and what are the energy related situations, or maybe the voltage related situations, voltage rating kind of thing, the frequency of LC oscillation matching with the frequency of resonance and all. So that kind of thing you have here. And if you try to see the day-to-day practical life situation, then the TV panel was working as series resonance circuit, but the remote we have in our hand, which is generating a kind of frequency of some fixed value. So that LC oscillation is essentially taking place inside the remote, which is generating EM waves of desired frequency. Now after this concept, let us discuss one leftover concept, that is called parallel RLC circuit, which we have not discussed in our second lecture of resonance, because this is a kind of thing which is gradually having less discussion, or maybe the questions involvement of this particular circuit is getting less. So we are covering this thing at the end. Let us talk about parallel RLC circuit. Let us talk about parallel RLC circuit. A typical format of parallel RLC circuit will be that you have a resistance, an inductor coil, and a capacitor, all of them connected in parallel to alternating EMF supply. You can see here, this is resistance, inductance and capacitance. There can be several variation of parallel circuit, but essentially the inductor and capacitor, they always happen to be parallel. Resistance may be in series with them, but these two are supposed to be parallel to each other. Now in a typical parallel circuit, remember that the EMF supplied to all of them is same, and the current in them will be having some phase involved. If you see that EMF is same, then if you remember that the current through the resistor, let us suppose it is having a direction like this, then the current in the inductor will be lagging. This is the kind of discussion you have already seen here. So the current in this circuit will be lagging the current through resistor by say 90 degree, but you already know that the current in the capacitor that leads by 90 degrees. So the current which will be flowing into the capacitor, that will be shown like this. All of them are being treated as vector quantities. Let us suppose at some instant we demand that what is the supply current which has gone from this place. This supply current is coming from here. A part of it is going in resistance, a part of it is going in inductor, a part of it is in capacitor. If you look at this situation, then the supply current will have the formula. It will be the vector sum of all these vectors, that is IR, IL and IC, the vector sum of all of them. So that will be making it IR square plus IL minus IC whole square under root. This is the kind of expression you will be having so long as this current is concerned. If you see the situation here, you can also say that the phase difference between the current through inductor and through capacitor, that is 180 degree. You understand? The phase difference, or you can say current through inductor and capacitor. Current through inductor and capacitor in parallel circuit are out of phase by 180 degree. Understand, the parallel circuit will be having current through inductor and current through capacitor out of phase by 180 degree. Now what is the meaning of this? Meaning of this particular thing can be understood if you try to consider an example. Imagine a situation in which I am giving you a resistance connected to an inductor and capacitor like this, and this is connected to an alternating source. Let us suppose at any instant it has been given that the current which is flowing through this inductor is 0.8 ampere. You understand? Current through inductor is given to you 0.8 ampere, and current through capacitor at any instant has been given to you as 0.3 ampere. ये हमें given है. The current through inductor is 0.8 ampere and current through capacitor is 0.3 ampere. And now it has been demanded that what is the supply current you have thrown into this circuit. Understand? So here essentially you can see the inductor and capacitor, they are parallel to each other. Maybe resistor is not parallel. ये pure parallel circuit count नहीं कर रहे हैं आप, but still you have inductor and capacitor in parallel. And you know that in a parallel circuit the current through inductor and current through capacitor, they are out of phase. So once they are out of phase by 180 degree, that means अगर इसमें करंट डाउनवर्ड डायरेक्शन में होगी तो इसमें करंट इसका मतलब अपवर्ड डायरेक्शन में होगी. दे आर फ्लोइंग इन ऑपोजिट डायरेक्शन. यू अंडरस्टैंड? अगर करंट यहां पे इंडक्टर में इस डायरेक्शन में जा रही है तो यहां पे कैपेसिटर में करंट अपवर्ड डायरेक्शन में होगी. इफ यू कंसिडर दिस पर्टिकुलर जंक्शन, देन रिमेंबर दैट फॉर एनी इंस्टेंटेनियस करंट और सो दी किरचॉफ्स जंक्शन रूल दैट इज वैलिड. अगर यहां पे 0.8 एम्पियर आ रहा है और यहां पे 0.3, देन यू कैन सी definitely the current which must have been approaching this junction must have been 0.8 minus 0.3, that is equal to 0.5. अगर ये डायरेक्ट करंट सर्किट का हमारा क्वेश्चन होता तो इसमें 0.8 और 0.3 दोनों ऐड करके आप यहां पे 1.1 एम्पियर लिखते. बट रिमेंबर दैट फॉर दिस काइंड ऑफ थिंग हियर मे बी यू कैन अज्यूम एज इफ द IR part is absent, it's only the IL and IC that is making the role. So that is 0.8 minus 0.3, and the supply current which you will be having here, that will be the subtraction of these two, and that will be 0.5 ampere and not 0.8 plus 0.3, rather it is 0.8 minus 0.3, that is 0.5 ampere current will be flowing into the supply circuit. Understand? Now as you had the concept of resonance for series circuit, the same kind of resonance you can have for parallel circuit, RLC circuit rather you can say, which you have here. So if you talk about the resonance of this parallel circuit, if you talk about the resonance condition in parallel circuit, then remember that the resonance frequency is same. You had for series, same kind of frequency you have for the parallel and series circuits. They are having the same resonance frequency, but here at resonance the situation will be entirely opposite to what you have in series circuit. In series circuit at resonance you had minimum impedance of the circuit, but in parallel circuit you have the other way around, that is the maximum impedance, the current is minimum, and there you were calling it acceptor circuit, but here you will be utilizing this thing as rejector circuit. That means for this particular frequency, since the current is minimum, so you can say the parallel resonance circuit is also called the rejector circuit. You understand? The parallel resonance circuit is also called rejector circuit. Is also called rejector circuit because at this condition because at this condition the current flowing into the circuit is minimum. The current flowing in this circuit is minimum. This is exactly opposite to you had for series resonance circuit. In series resonance circuit you have seen that at resonance frequency the current flowing into the circuit is maximum, rather you can say that particular frequency was accepted by the circuit, but here at that frequency the current flowing is minimum, or rather you can say that frequency is rejected by the circuit, and hence it is called rejected circuit. So that is all in our discussion. Before we move ahead, let us discuss what all we had in our today's lecture. In our concluding lecture of alternating currents, first we talked about the average power consumption in alternating current circuit, for which you got the standard expression P average is equal to E RMS into I RMS into cos phi, and we had several discussions based on that. It was said that this is apparent power, this is power factor, and how it can be involved with various resistors or inductors, how you call it wattless elements, what is the meaning of wattless current and all, and how you can calculate power on resonance condition. Then we had another very important setup which you called LC oscillations. This was a kind of circuit, you can say, which is used for generating any electromagnetic wave of desired frequency. Here also we saw that the frequency of EM wave generated, that has the same expression as the frequency of resonance, and based on that we saw how some energy oscillation is taking place and several questions based on that. Then we talked about the parallel RLC circuit, which involved low profile status, in the sense that very few questions are now asked based on resonance etc. of parallel RLC circuit. This was also called a rejector circuit, because at that particular resonance condition of this parallel circuit the current flowing into the circuit was minimum, and that was rejected, you can say. And at the end I must say that there were several solved examples based on the concepts involved here, and that essentially brought you to the end of the chapter of alternating currents. So now in the next chapter we will be talking about the concepts which are involved with the electromagnetic waves, and this is all for today. Thank you.